Hello everyone, I'm Xuelun from National University of Defense Technology. The topic of my paper is a novel location privacy-preserving task allocation scheme for spatial crowdsourcing. Crowdsourcing has gradually attached the attention of all walks of life, which defined as a company or organization posting problems on the network to collect better solutions. In contrast to general crowdsourcing, spatial crowdsourcing adds more location requirements that need workers to reach the designated location to complete the task. Spatial crowdsourcing often includes three parts: requester, worker, and crowdsourcing platform. First, requester publish tasks on the crowdsourcing platform. Then the crowdsourcing platform allocates tasks according to task's location and workers' locations, and then workers accept and complete tasks. With the rapid development of mobile internet technology, spatial crowdsourcing has also become popular. It plays a crucial role in various fields, such as news, tourism, intelligence, disaster response, and urban planning. Take real-time traffic condition monitoring as an example. It affects people's daily travel and lifestyle at all times. By obtaining the spatial distribution information of users at different times and corresponding various sense data, such software can analyze and speculate real-time traffic conditions. When users use this software, they passively become the crowdsourcing worker and share the information and sensor data. At the same time, people have paid attention to information security, hoping not only to enjoy convenience of emerging techniques, but also to protect their private information. When using crowdsourcing, the crowdsourcing platform needs the information of tasks and workers to perform task allocation, which usually contain a lot of private information. If it leaks out private information, disastrous consequences will spring out. For example, when users are enjoying the taxi service, they need to tell driver where they are and where they want to go, but users do not want the platform to know, because location data of user may indicate the home address, lifestyle, and other sensitive information. Attackers would know the real-time location of users once they grasp the privacy. This secure risk suppresses the availability of crowdsourcing and may let some people refuse to use crowdsourcing. Thus, it's significant to allocate tasks efficiently at the promise of protecting privacy. To solve this problem, many feasible solutions have been proposed. 13 use homomorphic encryption and use covered circuits to achieve a secure task distribution, but it only protects the privacy of workers without considering the privacy of tasks. However, task information will indirectly reveal the worker's information. 21 designed a grid-based position protection method for task distribution, but the distribution process involves heavy encryption and decryption operations, which is not efficient for practice. 23 proposed a novel spatial crowdsourcing framework without trusted third parties, but providing differential privacy guarantees. But workers need to set up an acceptable location in advance, which requires a relatively sizable storage space. 22 designed a data aggregation protocol based on k-anonymity, but it cannot well resist malicious deception of workers. Most of the workers focus on how to allocate tasks more securely and efficiently, but ignore the next step after task allocation, that is, how to deliver tasks to workers securely and efficiently. The major contributions of our article are as follows. First, we propose a scheme for spatial crowdsourcing task allocation based on the two-server model and an additively homomorphic cryptographic cryptical system. The proposed scheme protects the location privacy of workers and tasks without involving any online trusted third party. We put forward a novel method to deliver tasks and calculate the travel information securely. This method ensures that only workers who meet the requirements can get the location information of tasks and also allows workers to reconstruct task location with practical efficiency. Third, security analysis in our paper indicates that our scheme can protect the location information about the workers and tasks, as well as the data access patterns. Experimental results demonstrate that our scheme achieves critical performance in terms of computational overhead and travel cost. The scheme consists of four parts, namely key generation, data encryption, task allocation, and task delivery. In key generation, S generates PK and SK for the Paleo crypto system, and then send PK to CSP requesters and workers. And then workers encrypt their locations, and the requesters encrypt the locations of tasks, and then they all send the encrypted location to CSP. After CSP receiving requesters' tasks, then cooperated with SAS to calculate the travel message between tasks and workers, generating candidate worker list based on this. Finally, CSP notifies workers in the candidate worker list in turn until the task is assigned. Workers receive travel information about tasks after they accept tasks. Now let's introduce the calculation of travel message. And firstly, we will show the detail of distance calculation. After receiving the encrypted tasks locations and workers locations, the CSP cooperates with S to calculate the distance between tasks and workers. The calculation procedures are shown in algorithm 1. First, CSP used the homomorphic encryption property of the Paleo crypto system to calculate the coordinate distance values through step 1 complete by CSP. And then, in order not to let S get any information about the location, then choose two random numbers, adding it to the results and send the results to S. Upon receiving ABCD from CSP, because S has the decryption key SK, it can decrypt and calculate the corresponding squared distance, so S cannot get the real distance value. CSP can use the properties of homomorphic encryption to remove the influence of the random number in the results. Answer 3 and answer 4 are the squared distance in the x and y directions of the real distance between workers and tasks. Same as before, CSP select a random number to prevent S, and finally it can get the distance of workers and tasks. Before CSP notifies workers according to the list of candidate workers, it also needs to work with S to calculate the travel angle of workers. In this way, workers can combine their locations and travel angle to restore the location of tasks. After pre-processing, the payload crypto system can encrypt and decrypt any real numbers in the range. And now, let's introduce the detail of travel angle calculation. Similar to algorithm 1 at the beginning, we need to get the distance between the worker and the task first. The distance values calculated in algorithm 1 have been recorded in the worker database, so we can directly call the distance result value according to the worker ID in the candidate worker list. The same is to prevent S from getting any valid information from the intermediate results, and the effect of the random number need to be added, so E and F are calculated and sent to S. S decrypts the received information, calculates the division value tangent, and send the sign value according to the rules. It is not difficult to know that the results corresponding is mathematically explained by the tangent value. It should be noticed that when the longitudes of the 2 points are the same, the denominator is 0. Although this situation does not occur frequently, to implement the scheme smoothly, we use a very small value instead of 0 in the code. Finally, CSP can modify sin x and sin y value according to the positive and negative value of the random number, and it is the next information to be sent to workers, which is also stored in the workers database too. We devise efficient task allocation algorithm for both SAT and WTS. After the previous algorithm process, each task has a corresponding list of candidate workers. Therefore, the server allocation can directly notify worker in order according to the candidate worker list until the task is assigned. The procedures are shown in algorithm 2. In the SAT, the maximum number of candidate worker max NT is set to prevent too many workers who meet the requirements from affecting efficiency. Use counter to mark the number of selected workers, and TD task is the maximum distance D that the task T can accept. After the processing of source and available, CSP can get an optional and orderly set of workers. After many cycles, each task can get a list of optional workers. And now let's introduce the experiments of our scheme. We compare with other 4 schemes about location privacy preserving, protect workers and requesters, and the server is untrusted, do not need a trusted third party, using cryptographic approach, and don't fake workers' location. We evaluate the runtime under different numbers of workers and different schemes. Figure 2 indicates the time spent on the program under different number of workers. We can see that the time to generate the list of candidate workers increased continuously with the increase in the number of workers, because each worker needs to calculate the distance from task locations, and is based on encrypted data. It can be found that we leave all or most of the calculations to the cloud platform, and local workers only need to perform simple calculation to get the real location of the task. Figure 3 shows the time for the two schemes to generate a list of candidate workers under different number of workers. Our scheme requires fewer exponentiation operations than 21 and have more advantage. Figure 4 shows the number of candidate workers generated under different maximum acceptable distance when the maximum number of candidate workers is not set. So set the maximum number of candidate workers is necessary. Figure 5 and Figure 6 show the error value between the task location and the real task location recovered by the worker according to the information sent by CSP under different numbers of workers. Figure 5 is longitude error and Figure 6 is longitude error. It is found that error is not significantly related to the number of workers. The maximum error is very close to 0. Figure 7 indicates the longitude and the longitude error under different maximum acceptable distance. We can find that there is no particularly obvious rules. The error is tiny. The calculations in the workers' local are easy, fast, and highly accurate. That's all. Thanks for your attention.